inviting me. I think I've got a long-standing relationship with you now, and I like to feel that I'm part of the Martai family. For those of you who know me, you're probably expecting me to show some cutting-edge, prototype, high-resolution MRI, but today I'll be talking about something else which I've spent probably 15 years on, a bit more, and that's ways to non-invasively stimulate the brain for the treatment of mental illness. And I'll see if I can work out this clicker. Yay. So I've been in MRI for over 20 years, but also in the field of brain stimulation. So after I finished my PhD in 2005, I was based in a university department, but actually at a hospital, and it was in a department where we specialised in prototype brain stimulation for the treatment of mental illness, specifically major depression, but also other disorders such as schizophrenia, OCD, smoking cessation, autism. And so, not surprisingly, the media got onto this because back then in about, in about 2006, 2007 and 8, it was still quite new, and many psychiatrists were quite resistant to the idea that something like this might actually work. So I should point out that I was really fortunate to have a mentor for 10 years. This is Paul Fitzgerald, and for those of you who aren't familiar with Paul, he's he is almost #1 in the world, I would say, in terms of psychiatry and brain stimulation. So this is someone who's a quite gifted psychiatrist with a PhD in brain stimulation, responsible almost single-handedly for getting TMS Medicare rebatable in Australia from about 2021. He's published hundreds of articles on this, and so I've been really fortunate to have learnt what I know about TMS from him. So when we talk about brain stimulation for psychiatry, most people think of convulsive therapy, which is electroconvulsive therapy. That's almost a last resort, and I probably don't need to tell you, it's quite drastic under general anaesthesia, electricity, person's put into a seizure. It doesn't always work. Quite commonly, the person might be treated, but they'll be very flat. They have what we call as a flat affect, so their emotion can be very flat, and again, it doesn't always work. They might have some memory loss as well. More drastic than that is what we call deep brain stimulation. So you drill a hole called a burr hole, put an electrode in, connect electricity, stimulate parts of the brain. Again, that's quite drastic. What if we could do something similar? So in this case, I'm talking about major depression. And not just that, we call it treatment-resistant major depression. So the person has been on a number of types of antidepressants for chronic depression. This has gone on for years, sometimes decades, and their symptoms don't really seem to reduce much. Instead of ECT, we try them on transcranial magnetic stimulation. I'll see if I get the laser pointer here. So I'll show you a short video of exactly what I'm talking about. So this is now established. For years, I also helped research direct current stimulation. So we put pads on with saline water and connect very low current, very low amount of electricity to non-invasively stimulate the brain. We can also try optogenetics, and we also tried, and other people have obviously gone beyond me now, but using ultrasound. So there was a time when we thought that ultrasound could go through the skull. Most physicists would have agreed you cannot do that. We now know that's not true. You can put ultrasound through the brain for a variety of purposes. So I'll be talking about transcranial magnetic stimulation, but just be aware that there are other forms of brain stimulation that are not invasive, and by non-invasive I mean you're not drilling anything, you're not putting anyone under anaesthesia. It doesn't hurt them. The only thing they might feel is a slight touch on the scalp, because when we do it, we're depolarizing, we're firing not just brain cells, but sometimes the muscles on the scalp as well. So just a little bit of a tick. But we can also use another form, which I won't go into much, but this is known as a focused ultrasound. And depending on the intensity, we can stimulate brain cells, or we can burn tiny little holes to break circuits. So how did it all start? This wonderful person, Barker, in 1985 in the UK, an engineer was working on a technique to non-invasively stimulate the brain. Here he is in 1985 with his stimulator and his coil. And the story goes something like this. The colleague walked down the hallway and said, "How's your invention going?" And he goes, "Well, I think I've got something. I'm not quite sure how to test it." And he said, "Well, put it over my head." He turned it up and his arm flew up. So he put the coil over and his arm went, whoo! And so non-invasive brain stimulation was invented. And then they said, "Well, what are we going to use it for?" And now here we are 40 years later and we know exactly what we're going to use it for. And there's probably a variety of other instances as well. But the most common application is for treatment-resistant major depression. But it's also used for many other purposes, such as motor conduction. So we can time things from stimulating the hand and we put electrodes on and we see how long it takes. So we can do this most commonly for multiple sclerosis and motor neuron disease. As I mentioned, it was only Medicare approved 2 years ago, but it was approved for depression, anxiety disorders, and also obsessive compulsive disorders. And there's lots of evidence mounting, and hopefully it will lead to also Medicare rebatable treatment for Alzheimer's disease, schizophrenia, Asperger's spectrum disorder, chronic pain, eating disorders, and also addictions. And the evidence is mounting quite quickly. So how does it work really quickly? We have here a coil, and what's inside it is a whole lot of copper. And it looks like an infinity, but we call it a figure of 8. Why is it a figure of 8? Because if you do mathematical modelling, we have a peak just here. So if we do a figure of 8, this is our electromagnetic peak. It actually started, you can still use these big circular coils, but you don't target as precisely. You've got a bigger target. So we use that for things like vision. We put it at the back, we pulse it, and the person can see bright lights. We call phosphine. So this is very useful for looking at people with forms of vision impairment. So basically, we put electricity through the coil and we have a magnetic field created, as you can see by these loops here. So what are we actually trying to do? We know from over 20 years of research that we're actually trying to target neurotransmitters called GABA A and GABA B. Depending how we pulse the coil, so we can do, say, 1 every 5 seconds, or we can do up to 100 times a second. These will have different effects on different brain cells. And so it's really, we're trying to get this balance, not to simplify it, but it is a sort of balance between GABA A and GABA B. So we have neurons, and in between them are a whole lot of other neurotransmitters, and some of them are called GABA. And some try and stop the transmission, so they slow it down. Other ones facilitate it, they let it through. And we're trying to change this balance. But there are other things we have to consider. It's not as simple as just putting it on any part of the brain and just pulsing, because that won't really do anything. We have to consider how far away is the scalp from the top of the brain, because the further away the coil is, the more we have to turn up the machine. It's not just like we put the coil on and pulse it and electromagnetism comes through and we move. We have to titrate, and everyone's brain is shaped slightly differently on these curves we call gyri. Everyone has a different distance between the top of their brain, or the outside, the cortex, and the outside of their scalp. So we have to measure all these. And how do we measure them? From MRI. So we give the person a quick brain scan. Whoops, so here's a quick brain scan called a T1 weighted. And you can see here on the software, I've just used this line here like a caliper, and I've measured what is the distance from the top of the brain to the outside of the scalp. And we know for every millimetre that we move beyond that, it's roughly 3% of the machine. So we can titrate it up and down depending on what we call the scalp to cortex distance. So what does it actually look like? Let's see if I can play this. Oops, won't play. It was a quick demonstration. But what we can see here is this is a big stimulator. This is the coil. The person has 3 electrodes on their thumb here. And as we move the coil around over the part of the brain responsible for all our movement, our legs, our lips, our arms, etc., as we move around with the coil, different muscles will activate depending on which part of the brain we're stimulating. So why are we going for this strip here? Because we have this thing called the homunculus. And the homunculus is basically describing this person here. And the larger the part of the body means the more part of the brain is controlling that area. So unsurprisingly, we can see here that our mouth is very sensitive. We have a lot of control over it. And the largest control we have is our hands. And the largest part of our hands that we have control over is this muscle right here on the thumb. So we call these big muscles bellies. So we're going for the belly muscle. And we can see here the part of the brain that controls the belly is quite large. How was this discovered? Over 50 years ago, a famous neurosurgeon, Penfield, was operating and electrically stimulated very slightly parts of the brain while the person was being operated on. And different parts, different muscles were activated as he moved across this strip. So it's called various things, the precentral gyrus, Penfield strip, homunculus. So we're going for this little bit here. How do we know how to target that? Won't it take forever? No. Once you've done this maybe 50 times on someone's brain with a coil, you get very good at just walking up to the person, putting the coil on and doing it. Within probably the first 5 pulses, you'll probably get it really quickly. But I was a clinical researcher, so it wasn't just applying it. I wanted to know what I was dealing with because there's so many types of stimulators and coils and cables and coolers. So I worked at a hospital, so every time I got a new coil, I'd go down to emergency. This is a portable CT scanner, X-ray scanner. And so I'd go down to emergency, and this is a wireless X-ray detector. Very useful, obviously, in emergency, because the person can come into emergency. They'll be in their bay in the ICU or the emergency department per se. You put this detector under their back, you just slide it in, you move the X-ray machine over, and that's how you do an X-ray without taking the person to the X-ray machine. But I do it with TMS coils. This was one of our prototype stimulators in about 2007. So there's a lot of hardware in here. I was very lucky to work with a team of biomedical engineers, and this is one of our biomedical engineers upgrading one of the circuit boards for me. This thing here, called a capacitor, is what generates the electromagnetism. This can generate up to 2.2, we call it Tesla magnetism. So the very high-powered MRI scanner, which Marti has, is 3 Tesla, which is about 60,000 times the Earth's natural north to south magnetic strength, like we have on a compass. So instead of 3 Tesla, this is 2.2 Tesla inside this box here. So it's extremely powerful. But there's not just a figure of 8 coils. This is just an article that came out a few years ago showing 40 to 50 types of coils, which is quite extraordinary. So these are the coil designs, and these are the electromagnetic modelling. But the coil can only go about 4 to 5 centimetres deep. It's only for the top of the brain. What if we want to target deep parts of the brain? Well, there are coils for that, and they're called deep brain coils. So here we have one specifically designed to target a part of the brain that can help with major depression if regular TMS isn't effective. Another one targets the brain very deep for OCD, another one for smoking, etc. So this is our traditional. These are the deep coils. They're also called H coils. Why? Because they're developed by a company in Israel, and H, the Hebrew word is hesed, and hesed means wisdom. So they call it a wisdom coil. But there are lots of challenges in this. We don't just put it on and stimulate. The neurons in the brain don't just go up. They go on certain angles and orientation. And the coil has to be exactly 90 degrees to those neurons on a tangential. And so when we go up, we might get a little bit of a thumb movement. And as we move the coil maybe 1 degree, then we might get a big impulse. The brain is extremely sensitive, not just to electromagnetism, but to the angle of the electromagnetism. So we need very accurate positioning. I'm not sure how to go back on this. Oops. Can't seem to go back, unfortunately. We also need to know the distance, and we need very accurate placement per se. What if we can't get the exact placement? Well, generally what I do with every subject anyway, because in the end, my life is and always has been really about MRI, is I give them a brain scan. So here I am years ago, might look a little bit younger, with the person's brain scan on the screen. And what you can't see in this picture is I've set up a magnetic field all hooked up to an interface computer, and that talks to that thing which we call a magnetic wand. And as I move the wand around, I've actually got red X bars on this screen. So as I move it around, the X bars move on the screen as well. More so, I've also got numbers coming up here in all three directions. I know the exact number to a millimetre cubed of where that one little millimetre cube responsible for the right thumb is coming from. So this is called neuronavigation, because it's navigation of the brain. I do all this while the person's wearing an EEG cap as well, because while I give them stimulation, I want to measure the change brain activity. So this led to, obviously, an article. Proud to say, I think it was one of the first that was published in 2008, around there, with other people, of course. You can't do these things on your own. But we don't target the motor. Targeting the motor isn't going to help with mental illness. What does help is correct targeting over this area here. This is our higher order thought, executive functioning, and highly linked to the circuit, which is emotion, which we know is implicated in mental health. And we call it the dorsolateral prefrontal cortex. Why are we targeting this? Because all the MRI studies that have been done that show various mental illness disorders always show this area, this is differences in blood flow, in people that have some sort of illness versus those that don't have some sort of mental illness. It's always the same area. You can see here, dorsolateral prefrontal cortex. So here are some of our articles as well, which we've published on this. So as I said, it's linked to this circuit here, which we call the Pepez circuit, which was named after Pepez about 90 years ago. So it was only recently in vivo, in the MRI, with these new techniques that we can look at pathways where we could say, wow, in the living brain, not only is it real, but it's very healthy and it's linked just the way that Pepez said it would be based on postmortem. But we can go further than that. We can say, let's set up 1,000 different points in the brain, we'll call nodes, and then we'll measure from MRI how strong they are between each node. We're going to connect them all, so we call it a connectome. And then we can put it into the computer and say, based on the scan, show us in different strengths, so the width or the colour, how strong these different connections are. So this dorsolateral prefrontal cortex is linked to many parts of the brain, but it also has a direct relationship to the hippocampus. It doesn't actually go like this, it goes around and then from the back comes in. So the hippocampus is the most widely studied part of the brain, which is one of our oldest parts of the brain, which is directly related to emotion, and just happens to be what my PhD was on 20 years ago. So these are some of the articles that I've published over the years on TMS, and you can see it doesn't just come down to how successful is the treatment, it's what's involved in getting to the point to accomplish successful treatment. So this is looking at GABA, those neurotransmitters. This is a trial of people that had treatment based on their MRI scan versus no MRI scan, and there was a difference, a significant difference. So if you use MRI to localize where the treatment is, there's a much higher probability that the person will be successfully treated. This is, of course, is diffusion tensor imaging. This is where the EEG's placement should be, electromagnetic fields, etc. I see I'm running out of time. Does it work? Oh yes, at least 50%. And I had hundreds of people over 10 years that I helped treat, hundreds. And these were chronically ill, treatment-resistant, major depressive. So some people we had to pick up from inpatient, from hospitals, from private clinics. This is where these people lived because their depression was so bad for so many years, the medication really didn't help. At least 50%, we've published this many times, at least 50% of people after treatment were no longer depressed. In other words, their responses to questionnaires and their brain scans had changed at least 50%. So their symptoms had reduced by at least 50%. The treatment back then was 15 minutes a day, 5 days a week for 6 weeks. Now we can do the treatment in 2 sessions. That's just in the last 10 years how much we've learned about the brain and magnetic stimulation. I really like this photo because I treated a person and after 2 sessions, so 2 lots of 15 minutes, she said, take the coil away. I haven't felt like this in decades. Quite astounding. And the next day she came in with a TMS cake that she'd baked us. But the days of breaking my back, standing there, making sure that when the person breathes or sneezes, I'm doing the coil with them. We can do it all with robots now, as you'd expect. So they're all automated. You feed in the brain scan. You put markers on the person's head. The robot does the rest. This is the lab that I had many years ago. So it started off with a mannequin, which we'd basically put a towel on and dip with saline and then connect a battery to it to create, with an oscillator to create artificial brain waves and all this sort of stuff. It was pretty crazy. We can also now do it in the MRI. So to localize the exact target, instead of using the brain scan, taking them out of the scanner, taking them to the lab, hooking up the magnetic field, we can do it all in the scanner, and we can scan them and then treat them. And we can do it interleaved as well. Scan, treat, scan, treat. This is an example of the brain change when you're moving your thumb. So we have a huge influx of blood to replenish the glucose and oxygen because you're using brain energy, essentially. And we've moved on. We can now do sub-millimeter, so beyond 1 millimeter accuracy on neurons to look at a group of neurons to see how the electric field is changing the neuron activation. It's also being used for other disorders, as I mentioned, such as stroke and dementia. How's it doing this? It's slowing down progression of disease. And after a stroke, obviously the brain will try to recover. TMS has been shown that it can help it can accelerate the recovery trajectory. Other things, so a lot of my ideas are a bit out there. So years ago, I published this article on ear wiggling. I don't know how many of you can ear wiggle, but I'm fascinated by ear wiggling, I think because I can do it. And I taught many people how to do it over the years, and I thought, what if I could do it with brain stimulation? If I could do it with that, then maybe I could help with stroke recovery as well. So where is ear wiggling located? No one knows. So I did an experiment. I jumped in the scanner. Someone else was controlling it, obviously. Did a functional task where every 5 seconds a light came up and I wiggled my ears for 5 seconds and then stopped wiggling. And eventually you get the activation. And believe it or not, I was actually able to predict which part of the brain was responsible for ear wiggling. So the point was, I proposed that if you target that part of the brain for ear wiggling and you make people ear wiggle after stroke, then you could potentially accelerate the recovery. So here's my brain scan, and here's the pathways for ear wiggling. And lo and behold, it goes to the dorsolateral prefrontal cortex, among other parts of the brain. So in a nutshell, we can now personalise TMS for every person rather than a rough, here's the threshold, we move it forward roughly to this area here and treat them. That's in the past. It's now personalised medicine. Everyone has their unique spot, their unique angle, unique depth, unique threshold. We have to take lots of things into account, of course. And that's it. I know I'm over time, but